In this unit, we're going to begin talking about some networking topics with Microsoft Windows, and we'll continue with this theme throughout the rest of the quarter. So we're going to talk about networking with Windows, but in order to do that, we have to understand some of the technologies and some of the standards that underpin networking, and this, of course, is utilized by Microsoft Windows. So it's important to have a strong understanding of things like Tcpip, which we're going to talk about. We'll make sure we understand IPv4 addressing, and we'll talk a little bit about IPv6 addressing as well, and some ways that we can work with IPv6 even in our IPv4 networks. So we'll talk a little bit about that, tunneling, tunneling IPv6 through IPv4 and so forth. So first, let's talk about TCP/IP. So TCP/IP, it stands for the Transmission Control Protocol and Internet Protocol. And it's basically a standard or a protocol standard. It's designed to deliver packets to computers on any scale of network, from a small network in our corporate environment all the way up to the World Wide Web and the Internet, the larger network of networks that we call the Internet. So it's a suite of protocols that have addressing, logical addressing, and physical addressing, and we'll talk about that in just a few minutes. We have name resolution as part of TCP/IP, or it's one of the protocols within TCP/IP. Dynamic address assignment, so we don't have to configure these IP addresses. Efficient and reliable packet delivery, packet sequencing, and many other tasks. So it's the default network protocol installed in Windows, and Windows supports natively in 2012 both IPv4 and IPv6, which we'll talk about a little bit more detail later on. So some of the protocols that we rely on in networks, which we're going to talk about in the rest of the course, DNS is one, DHCP, which allows us to auto-configure network interfaces on our computers. We'll talk about TCP and how that helps us deliver packets. UDP, which is slightly different than TCP, so we'll talk about those differences. And of course, the addressing on our networks, which is IPv4 and IPv6, and those are logical addresses. We'll talk more about physical addresses, which we use ARP with the physical addresses, so we'll talk more about that in a little bit. And ICMP, which allows us to do troubleshooting and to see how packets are being routed on our network. We could do the same thing with ICMPv6. So TCP/IP is a standard that was developed in the early 1980s, late 1970s, early 1980s, and if you read the RFP on TCP, you'll see that it has 6 basic goals. The first is basic data transfer. So TCP should be able to transfer a continuous stream of octets in each direction between its users by packaging some number of octets into segments for transmission through the internet system. That's a mouthful, but it says a lot. Basically, we need to have a protocol that's going to facilitate the delivery, the reliable delivery of raw data, basically. That's what they're talking about when they say octets. It's the raw data. So we're not concerned with what that data is, just that we have to get it reliably from point A to point B. And reliability is the next piece. So the TCP protocol, it has to be able to recover from data that's damaged, lost, duplicated, or delivered out of order by the internet communication system. So the internet protocol, by just the way it works, it's not very reliable. So by layering TCP with the internet protocol, we can sort of create that reliability. So some tricks we can do to ensure that we have that reliability. Flow control basically refers to you don't want to overwhelm a sender or receiver. So if a sender can send faster than a receiver can process, flow control prevents that from happening, because that would be lost data. If we're sending the data too fast for someone to handle it, then we lose it. Just like in a classroom, if we're delivering content too quickly for students to be able to take notes or something like that, then that data is essentially lost, or that information is lost. So we want to have some method of flow control to keep tabs on how quickly we can send that data. So TCP allows us to do that. The next thing is multiplexing. So without something like TCP, if you think about it, in the old days, most homes had one telephone. And if you called somebody, at a house on a telephone, everyone had to share the one line. So you essentially had one phone number to call somebody in the house. Of course, it's not a good analogy today because most people don't have home phones anymore. But that's kind of how IP works. You have one IP address to a machine typically, though you can have multiple IP addresses. Just like in the old days, we could have multiple telephone lines. But what if we could somehow share that same line with multiple people, and we can all have conversations at the same time? And that's what multiplexing is. So multiplexing allows many different applications to use the same underlying communication lines. So we'll talk a little bit about multiplexing and how that works later on. And then connections. So with TCP, we should be able to use IP to create a connection between 2 points. That's an established connection, which we can't do with just pure IP. So TCP allows us to create connections. So that way, once we establish a connection with a peer on a network, that communication is sort of a known session. So we have some context in how those packets relate to one another. And then finally, we have precedence and security. The security features that are discussed in the RFP for TCP are not to be confused with security features in network firewalls and things like that, which we'll talk about later on in this course. But there is some limited security capability baked into TCP, things like checksums and whatnot. And then precedence. So there is this idea of precedence in TCP. In other words, what is the priority for delivering packets? So, and these are directly out of the TCP, the TCP RFP rather. So you can go read this RFP and you'll see these exact same sentences where it describes each one of these. TCP is not a complicated protocol. You can go and read the RFP, and I think most of you would probably be able to follow it and would probably fully understand what they're talking about. So I certainly encourage you to do that, to go and take a look at the RFP and peruse the standard. So basically, when the way TCP/IP works, so when a user opens up a web page, a DNS request is sent to resolve the website name to an IP address. We're going to learn about IP addresses here in just a few minutes and how they work. So once the client gets the IP address with DNS, then it determines whether the address is on the same network or if it's on a different network. If the client's on the same network, the client requests the MAC address, or the physical address of the web server. And then it just it establishes a connection directly with the web server. If it's not, then the client sends the request for the web page to a router or a default gateway. And then the router or default gateway handles going and finding that node either out on the internet or on the local area network or what have you. But all of that's transparent to us, to the user. All they know is they go to a web address, it automatically finds the IP address and brings up the web page, whether it's on the LAN or on their local network, or it could be out on the internet somewhere. So routers are those devices that forward those requests to other routers until the request reaches a router connected to the web server's network. A lot of this should be reviewed from other courses where you've probably talked about TCP/IP in a little bit more detail. And if you haven't yet, I'm sure other courses will cover TCP/IP in great length. So I am kind of covering this very briefly here. So some general terms that you'll hear in networking classes, and again in this class, you have a MAC address, which is the physical layer address that's part of the network interface card. Every computer has a NIC and it has a MAC address, which is the physical address. The frame is the unit of data that we send at the physical layer with MAC addresses. And then when we step up to a packet is a network layer unit of data. So that's that's IPv4, IPv6. So packets refer to the networks, and most of us call everything packets, right? You'll hear people call things packets, even if they're not actually referring to a packet, right? So a frame and a packet and a segment are different. A frame is at the physical layer, a packet is a unit of data at the network layer, and the segment is a unit of data at the transport layer, which is above the network layer. If you recall from other classes, you've probably seen the layers. The OSI is the one that they seem to always show, but the TCP layers are application at layer 5, followed by transport at layer 4, network at layer 3, and then the data link layer at layer 2, and then the physical layer at layer 1. So basically at the very lowest level, you have a frame. Then the next layer above that, which is the network layer, you have a packet, and then transport is the segment. And then, of course, you have the application layer at the top, which we don't really get into in networking courses. But that's certainly something you would learn about in programming classes and things of that nature. So TCP or UDP basically has a header. So when we create these segments, the segment has a header that has information about that data unit. So TCP, they both use port numbers. This is what supports multiplexing. So when I talked about multiplexing and being able to connect to multiple applications at the same time on the same IP address, TCP and UDP allow that to happen through multiplexing, and that's done with a port number that's in the header. So a port number is really nothing more than an identifier in the header as to which port you want to connect to on a server or on an IP address. So the Internet Assigning Numbers Authority has dedicated port numbers for very well-known network services, and you may recognize some of these. For example, port 80 is the web or web pages, 443 is HTTPS or secure web, And there's a bunch of other ones on here as well. We'll learn about DNS, which is by default on port 53 with UDP. We'll learn about DHCP in this course as well, which is port 67 and 68. And we'll talk about some of these others as well later on. So certainly this is just a very short list of these port numbers. There are thousands of dedicated or well-known port numbers. I think most of them are below 1024, although there are many that are being assigned above the 1024 space as well. And you can go look these up. Again, they're all in RFP actually that you can go look at. So the functions of IP, basically the Internet Protocol is what does our logical addressing. So a MAC address is a physical address that's assigned to a physical device like a NIC card, and then the logical addresses are basically how we find devices on the wider network. We don't have to have visibility to every single network to know how to get to IP addresses. So it ensures efficient packet delivery, provides the information needed for packet routing. So logical addressing is where we use IP, and we can use IP addresses to map to MAC addresses when it's needed. But it's, these MAC addresses or physical addresses can change throughout the process. If you think about sending a piece of mail, an article of mail through the U.S. Postal Service, if you take a letter and you address it to someone, the first place that letter goes to is the only thing you're concerned about. So when I address a letter, all I have to do is find a mailbox that I know is going to get to the U.S. Postal Service. From there, it's completely transparent to me. But once in the United States Postal Service, the Postal Service is concerned about the physical locations of that letter. But I'm not really that concerned as a consumer. All I know is I address that letter, and it eventually gets to where it's going. But in between, there's this routing that has to happen within the post office, and that would be like the physical layer or the MAC address layer, those physical addresses where they're taking it from one sorting and processing center to another. But as far as I'm concerned, I only care about the logical address, where I actually want that letter to go, and eventually it should make it there in most cases. So the IP address is used to mainly find the network a computer is connected to. So again, if you think about the analogy with a letter, when you address a letter, you have a zip code and a city and a state, and those things are very high level. They tell the post office roughly where that letter needs to go. But then as far as delivering it to the actual physical address, that falls to the letter carrier on that route. No one beyond that letter carrier really cares about the physical address. Everyone else is looking at those more higher level addresses. And an IP address is very similar in that sense. Part of an IP address tells us what network we need to get that packet to. Once it arrives on a router that owns that network or that's responsible for that network, that's like our letter carrier that's delivering it to an actual mailbox on that network, delivering it to an actual machine in this case. So an IP packet always has a source IP address, in other words, where it came from, and a destination IP address, just like a letter that we send in the mail. We have a return address, and we have the address to which we want the letter sent. We do the same thing with IP. When we have an IP packet, it'll have both the source and the destination address. A unicache address is an address in a unit of a network data intended for a single destination computer, which is pretty typical to use unicast addresses. All right, so an IP is designed to deliver packets efficiently. It does not have a lot of features or for guaranteed delivery of large amounts of data, and this is really what TCP does for us. So IP, the important takeaway here is that IP is our sort of low-level standard that really just tries to do its best to efficiently and quickly deliver a packet from point A to point B. But it doesn't care about what order it's delivered in. It doesn't care about, it just takes its best effort. It doesn't care, if it loses something, it's not going to fret over it. It just gets lost. But we have to have some other protocol that's aware of that, and that's what TCP does for us. So IP is concerned with delivery of each packet that makes up a file, but not delivering the file as a whole. So it doesn't have the view of an entire, it doesn't care about the actual data. What it cares about is the raw ones and zeros that get passed down to it. And that's all it's going to care about. That's all it delivers. So it's a very, very simple protocol. It relies on TCP to ensure reliability, as I stated before. So routing packets is basically the responsibility of the Internet Protocol. So routers use destination IP addresses in each packet to determine which network the packet is sent to. So every time a router receives a packet, it's going to try to determine what the next network is that it has to connect to. So take this image as an example. We have a computer on network 1, host 1.1 on the upper left. And we have a computer on the lower right, host 4.1. So that's on the right-hand side. If I want to deliver a packet from host 1.1 to host 4.1, When it arrives on router A's job is to try to figure out which of those two routers is the most appropriate to deliver that packet to get it to router E. And it doesn't even need to know who router E is. It just needs to know which one of those two has the ability to get the packet there. Now, theoretically, if router A sends the packet to router B or C, it can still get to E. But it's obviously more efficient to route it to C, and then C will take care of routing it to E. But if, of course, if the line is disconnected between A and C, it can still go to B and then to C and then to E. So we have routing tables and routers that basically determine what networks they can get to. And that's how it determines where to deliver that packet. So it's kind of a complicated mesh of these routing rules that basically tell a router where they can send packets to get those packets to deliver to a host. And that's basically how routing works. You could take a whole class on how to do routing. We don't really talk much detail about routing in a Windows course because Windows is not really a router. Although that said, there are people who have turned their Windows servers into routers. You can have multiple interfaces on a Windows server, and theoretically you could route packets, but definitely not the most efficient way to do it. It's better to use a router to do that. But as network administrators and IT professionals, it's good for us to understand, even if we're not going to be working with routers, to understand roughly how they work and how they fit into the larger picture. So in the next slide deck, I'm going to talk about IPv4 and IPv6. So we'll cover internet addressing and those two protocols for internet addressing.